Welcome to this web note on compact metric spaces. This is a continuation of the study of this natural topology on the metric spaces that we defined in any metric space as a mirror image of the topology on the real line. Here in this web note we will try to characterize compact metric spaces and the properties of compact metric spaces. First of all, let us set the stage here. Throughout, let MD be a metric space. Let K be a non-empty subset of M. Recall the definition, the topological definition of compact spaces. K is said to be compact if and only if for any family O alpha alpha in gamma of open subsets of M that covers K, in other words, such that K is in the union of all the O alphas. Then there exist finitely many of them. There exist alpha 1, alpha n, such that in gamma, such that K is in the union of O alpha 1 union O alpha n. So we only need finitely many of them. That covers. A quick remark here: if we focus on the size of gamma, in other words, how many elements are in gamma, and we control and we say only the families with a size less than. This definition, of course, does not make sense if gamma is finite. So this definition of compactness only when you have infinite gammas. So the first one that you're going to meet is the countable one, the cardinality of n, and then of course the next one will be the cardinality of r, etc., etc. In other words, aleph 0 and aleph 1, and so on. So if you put a limit on gamma, on the size of gamma, you get a new concept, which is countable compactness, or aleph 0 compactness, aleph 1 compactness, aleph 2 compactness, etc., etc. And it's clear in topological spaces you can easily build a space where it is aleph 0 compact, but is not aleph 1 compact. So etc., etc. But what's going to happen is that in this setting in metric spaces, we're going to see that compactness for any cardinality reduces, of course, to aleph 0 compactness. So if you are countably compact, you are in fact compact. It's really amazing. This is, again, one of these deep properties of the topology of metric spaces. By duality, by taking the complement, we can also come up with what's known as the Cantor intersection property. Okay, let C alpha be a family of closed subsets of M such that C K, sorry, such that K intersects the intersection of all the C alphas is empty. In other words, there are no common points between all the C alphas and K. Then K does not mean finitely many of them. So, okay, then there exists alpha 1, alpha n in gamma such that K intersect C alpha 1 C alpha n is empty. Or equivalently, if K intersect any finitely many of them is not empty, where gamma f is any finite subset of gamma, then K intersects all the C alphas. So sometimes we'll see that these three properties, these three definitions of compactness are very useful. We can use the open set, we can use closed set in these two forms, and later on when dealing with Banach spaces or normative vector spaces, these three definitions are very, very useful. So let us start next to take, let K be a compact subset of M. Now we are going to study compact metric subsets of a metric space, compact subsets of a metric space, to see what kind of properties, deep properties they have. Okay, so let epsilon be positive. Obviously we have then K is a subset of the union of all the open balls where X belongs to K. This is true. Since open balls are open, then there exists, then, because K is compact, there exists x1, xn in K such that K is covered by union B open xn epsilon. So you see, K can be covered by finitely many open balls, okay, centered in K with radius epsilon given that epsilon. Okay, so this implies a property known as totally bounded. So again, here if you take the definition, okay, definition, K, let K be a subset of M. M is the matrix space. K is totally bounded if and only if for every epsilon there exists x1, xn in K such that K is in the union of xi epsilon I between 1 and n. Here we can assume that these points x1, x2, xn are in M and not in K, and have the original, a general definition of totally bounded. But since we are studying here in this web note compact metric spaces, we know for sure that in the case of compact metric spaces, this element will be in K. So we are going to restrict ourselves to the case where the element belongs to K. So what we proved now is that if K showed that if K is compact, then K is totally bounded. Okay, next, let us just make a little remark here, interesting remark. let K be totally bounded. According to the definition I just gave above. Subset of n, subset of n. Let epsilon equal 1 over n. Then, by definition of totally bounded, there exists x1 n, x phi n, and in other words, finitely many points in K, such that K is a subset of the union of the open balls x n I epsilon 1 over n, where I is between 1 and phi n. So this is just definition of totally bounded. Now let D be the union over n of these xi's, the centers that we just found, xn1, xn2, all the way to xn phi of n. So we have now a set which is a countable union of finite set, therefore it is countable, so D is countable. Next, let us prove, in fact, that D is dense in K, because these are elements of K. So D is, we have D subset of K, okay? And let us prove that it's dense in K. Let X belongs to K and epsilon positive, okay? So let us prove that D and the open ball do have something in common. There is an intersection, and this will show that the D in fact is a dense subset of K, or as we know it, the terminology is that K is separable. So compact subset will be totally bounded, will be separable sets. You have a countable set which is dense in K. So how do we prove that? So since we can find there exist n0 such that 1 over n0 is less than epsilon, and now we know that K is in the union of the open balls centered in x n0 I 1 over n0 I between 1 phi of n0. So there exists I less than phi of n0 such that x belongs to the open ball 1 over n0. Okay. Clearly, we got, in fact, xi n0 in the open ball x 1 over n0, which is included in, so xi n0 belongs to D intersect the open ball x0, which proves what we wanted. So a compact metric space is totally bounded, therefore it is a separable set. We also know from topology that it's well known that if K is compact, then K is closed. In metric spaces, we have a little bit more. We have the following theorem. Okay, let K be a compact subset of M, metric space, then K is complete. Okay, indeed, let Xn be a Cauchy sequence okay, in K. Set an equal xn, xn plus 1, etc. Then an is a sequence of subsets of K, which is decreasing, Okay. Let, moreover, since xn is Cauchy, we have that, moreover, the limit of the diameters of an when n goes to infinity is equal to 0, where the diameter of any set, as we have defined in a previous web note, is the sup of the distance xy when xy belongs to A. Now, we know also that the diameter of a set and its closure are the same, and therefore the sequence, okay, an bar is decreasing, and obviously K intersect an bar is not empty, because an bar contains an and is in K. K is compact, therefore it's closed, so it contains the closure of an. Okay, this implies then, since K is compact, the contour intersection property, or that the K intersect of all the an bars, is not empty. Okay, let X belongs to all the an bars, okay, which is also a subset of K. So X belongs to K. We have the distance from xn to X is less than the diameter of an bar, which is also equal to the diameter of an, which implies limit of the distance of xn to X is equal to 0 when n goes to infinity. In other words, that the sequence xn converges to X. So any Cauchy sequence is convergent, or that K is complete. The following property is truly amazing and will help us establish one of the deepest characterization of compact sets in a metric space. Let's call it here technical lemma. Before that, let us define, say, that K is sequentially compact if and only if any sequence in K has a convergent subsequence with the limit in K. So K is sequentially compact if and only if any sequence in K has a convergent subsequence which converges to a point in K. This is one of the on the real line, one of the simple in real analysis that students have learned, which has that every time you take a bounded sequence on the real line, then it has a convergent subsequence. So this is somehow similar. In other words, you have some kind closed intervals will be sequentially compact. So the technical lemma states the following. Let K be sequentially compact subset of M. Let O alpha be any family of open subsets of M such that they cover K. Then, this is truly amazing, then there exists epsilon positive, epsilon 0 positive, such that for any x in K, the open ball centered in x with is in some O alpha for some alpha. So there exists an alpha in gamma such that the open ball is with radius epsilon 0 is in O alpha. Proof of this, assume not. Then for any epsilon positive, there exists x epsilon in K such that the open ball is not in O alpha for any alpha in gamma. So you cannot cover, no O alpha will cover the open ball centered in x epsilon with radius epsilon. So let us take epsilon equal 1 over n. So there exists xn in K such that the open ball with radius 1 over n is not in O alpha for any alpha in gamma and n greater than 1. So this allows us to build the sequence xn. So now we said that K is sequentially compact. Therefore, there exists a subsequence x phi of n of xn, which converges to some x in K. Since the O alphas cover K, there exists alpha 0 in gamma such that x belongs to O alpha 0. O alpha 0 is open. Since O alpha 0 is open, there exists epsilon positive such that the open ball radius x and epsilon is in O alpha 0. Now, note for n large enough, we have the open ball centered in x phi of n, 1 over phi of n, is in the open ball x epsilon, because epsilon is positive and the x phi of n converges to x, so you do have this through the triangle inequality 1 for n large enough, okay? Which implies that the open ball x phi of n, 1 over phi of n, is in O alpha 0, which is a contradiction. So in sequentially complete subsets, you have this a beautiful property that for any open cover we have this epsilon that depends on the cover, by the way, such that for every element in the set, the open ball centered at any element in the set will be in one of the O alphas. Let us make a little remark here, because we have been talking about totally bounded. Note that if K is sequentially compact, then K is totally bounded. Indeed, assume not. Therefore, there exists epsilon 0 positive such that K cannot be covered by any finitely many open balls centered in K with radius epsilon 0. Cannot be covered by finitely many open balls centered in K with radius epsilon 0. Okay, so let x1 in K, since K cannot be covered by, so there exists x2 in K such that x2 does not belong to the ball, or that x1, x2 is going to be greater or equal than epsilon 0. So now assume x1, x2, xn are known. We know from the assumption, we know that K is not in the union of the open balls xi epsilon 0. Let xn plus 1 in K such that xn plus 1 is not in the union of these open balls. By induction, okay, by induction, there exists a sequence xn in K such that the distance from xn to xm is greater than epsilon 0 for any n different from n. So this is what we call an epsilon 0 separated sequence. There is no doubt that if we take any subsequence of this sequence, it will be still epsilon 0 separated, and therefore xn, and this is one of the properties of the epsilon separated sequences, xn has no convergent subsequence. No convergent subsequence. Which is, of course, a contradiction, since we just said that we are sequentially what? Sequentially compact. K is sequentially compact. So if K is sequentially compact, then K is totally bounded. Next, we are ready to prove now the main result of this web note, the main theorem, beautiful theorem. Let K be a non-empty subset of a metric space M, then K is compact if and only if K is sequentially compact. Okay, proof. Okay, assume K is compact. Let xn be a sequence in K. Set xn to be the closure of xn, xn plus 1, etc., which is a subset of K. Clearly, xn is decreasing. Then the intersection of the xn's with K is not empty. Since they are in K, we can drop K. Let x be in the intersection. Okay. Clearly, for any epsilon, so x belongs to xn for all n. And since xn is the closure of the set, then for any epsilon positive, the open ball centered in x intersect xn, xn plus 1, etc. is not empty. Because x is going to be a limit point of this set, and therefore there exists a sequence from the set which converges to x, and that's how we can get this. So in particular, let epsilon equal to 1, then there exists xn1, n1 greater than 1, such that x n1 belongs to the open ball x and 1. Let epsilon be equal 1/2. There exists n2 greater than n1 plus 1, because we said here for every n, the intersection that we have here, right here, for any epsilon, this is true for any n. So we can take n1 plus 1, then there exists n2 bigger than this, such that xn2 belongs to the ball x 1/2. By induction, there exists, we can build by induction there exists subsequence, there exists a subsequence x phi of n of xn such that x phi of n belongs to the open ball x 1 over n. So clearly this shows that x phi of n converges to x in K. So any sequence in K has a subsequence which converges to a point in K, and therefore K is sequentially compact. So K is sequentially compact. Conversely, assume K is sequentially compact. Okay. Let us prove that K is compact. Let O alpha be an open cover of K. K is in the union and O alpha is open for any alpha in gamma. Since K is sequentially compact, there exists epsilon 0 from the technical lemma such that for any x in K, the open ball is in some O alpha for some alpha in gamma. Of course, alpha depends on x. Next, okay, we have seen in this remark, that if K is sequentially compact, then K is totally bounded. So we're going to use that. So next, we know that K is totally bounded. And therefore, for this epsilon 0 that we found, there exist finitely many points in K such that K is covered union open ball centered in Xn epsilon 0. Okay, but for any I equal 1, 2, all the way to n, there exists alpha I in gamma such that the open ball, this is of course the technical properties we said just above, xi epsilon 0 is in O alpha I, so K is going to be in O alpha 1, O alpha n, which means that K is covered by finitely many O alphas. K is compact. So we took any family, open family, and we showed that from that family we can find some family that covers K, therefore K is compact. So this shows the main result, beautiful result, which says that countable compactness, which is, by the way, captured by the sequential compactness. It's very easy to see that sequential compactness. Of course, we're not talking about countable compactness from a topological point of view. We have to be very, very careful about what we mean by sequential compactness in the case of topological spaces. It has to be very well defined and very careful about that. In any case, so if we take countable compactness in the case of metric spaces, it is exactly the same as sequential compactness. And now we see that sequential compactness is the same as compactness, and therefore countable compactness is the same as compactness. It does not matter. All the cardinalities here will collapse to the countable one, aleph 0. Let me just make a remark here that I did mention before, but let me make it a little bit. In R, okay, bounded and totally bounded are the same. So, and by the way, this is also true not only in R, also true in Rn. Okay, so the concept of bounded and concept of totally bound are the same. But if you go to infinite dimensional spaces, for example, here if we take the general metric spaces, this is not true, and that's what I said. So I said we can take an infinite set with the trivial distance or the discrete distance and show that it's not the case. But let us take another example that will be useful in Banach spaces as well as normed vector spaces. Let's take M equal xn bounded sequence in R. So bounded sequences in R. And let us define the distance between two sequences xn, yn to be the sup of the absolute value of xn minus yn. Okay, so it's very easy to see, easy to check M, D is a metric space. Okay, in fact, it is complete, and the way to see it is to take a sequence of sequences, of bounded sequences, elements of M, which is Cauchy, and then you show that component-wise they are all Cauchy, they do converge, and then because you are in R, and then you go back to the definition of Cauchy in M to show that if you take the limit pointwise, the sequence, that's the limit pointwise, will be the limit of the sequence, and it's bounded, by the way. You can show all this. So it's quite tedious, but it's not very complicated. In any case, if we take now, take K to be xn's, such that xn's are between 0 and 1. Okay, so it is bounded. K is bounded. Because if you take the distance between any two elements, you can show that this is less than 1. So the diameter of this set is less or equal than 1, in fact it's equal to 1. And so it is bounded, but it's not totally bounded. Okay? Indeed. Set En to be the sequence 0, 0, 0, 1, 0, 0, etc., where 1 is on the nth term. So for example, E1 is 1, 0, 0, etc. E2 is 0, 1, 0, etc., etc. Okay, so this sequence En, what we have is, they are all in K. So for every n, En belongs to K. And the distance from En to Em is equal to 1, for n different from m. For any m different from m, the distance between En and Em is equal to 1. So number one, this of course shows that K is not sequentially compact. Okay, but in any case, we want to show that it's not totally bounded. And so let epsilon less than 1 have, okay, then K cannot be covered by finitely many. If K is covered by some finitely open x1 epsilon union be open xn epsilon, then one of the open balls here will have many ENs. Okay, but in this case, the diameter, which will imply that the diameter of this ball will be at least 1. So 2 epsilon should be greater than 1, and that's contradiction without choice of epsilon. Also, since this is one separated sequence, K is not. So here, this sequence K, the sequence En also shows that K is not sequentially compact. Note that K is closed subset of M. So you have a closed bounded subset of M that is not sequentially compact, therefore it's not compact and is not totally bounded, though it is bounded. So the property on the real line, which is that closed and bounded sets gives us exactly the compact subset of R, this property does not extend to any metric space. So the family of compact subsets of R, so here, if we look at, if we say notation, let M be a metric space. So let us introduce the notation K M to be the compact subsets of M. So we know that if we take R, these are closed and bounded. Okay, but that's not the case in any metric space. So we cannot. So if you take K of M, okay, it is included in closed and bounded. But we have to be very careful. This is not equal. Thank you. And in the subsequent webinars, we'll see more about compact sets.